Hello and welcome to yet another lecture on power generation and economics. Paper code EE704C. Myself Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is unit commitment solution methods. Today, I will discuss about Lagrange relaxation. Lesson objective. After end of this topic, student will able to understand the concept of unit commitment solution using Lagrange relaxation. So unit commitment solution methods using the conception of Lagrange relaxation. Lagrange relaxation solution. So generally, this method is based on a dual optimization approach. So let us, we are defining the variable called UIT as UIT equals to 0 if the unit I is offline during the time period T. Here the I, which stands for the unit, the number of units, the first unit, second unit, and T, that is stands for the period, that is for the first hour, second hour, third hour, fourth hour, in this way. And UIT equal to 1 if the unit I is online during the period T. So when this particular variable UIT is 0, means the unit is in offline condition, is offline during the time period T. And when UIT is equal to 1, the unit I is online during the period T. So now we can define the several constraint and the objective function of unit commitment problem. So the loading constraint can be written as P load T, that is the total load, minus summation over T equal to 1 to N PIT UIT equal to 0 for time period T equal to 1 to T. This is the loading constraint. Unit limits, that is UIT PI minimum less than equal to PIT less than equal to UIT PI maximum for the values of I equal to 1 to N, that is the N number of units, and the time period, that is T equal to 1 to T, the total time period is E in caps. So this is the unit limits. Another is called the unit minimum up and down time constraint. Note that other constraint can easily be formulated and added to the unit commitment problem. This includes the transmission security constraint, generator fuel limit constraint, and the system air quality constraint in the form of limits on emission from fossil fire plants, spinning river reserve constraint, etc. The objective function is summation over t equal to 1 to t, that is the summation over the entire time period. We are considering the time of first hour, second hour, third hour up to our t, and this is the summation over 1 to n, that is all the units. So we have 3 units, so it will be 1 to 3 if I pi to the power t, if I pi to the power t plus the startup costs of it, the total summation into uit equal to is a function of if, that is the is a function of pit and uit. This is the general objective function that we have. So we can form the Lagrangian function similar to the way that we have did in case of the economic dispatch. We can easily find the function of Lagrangian. So Lagrange function can easily determine, this is the Lagrange function, and it is a function of pu and lambda. It is The objective function that we have seen, this one that we have seen in the previous slide, f is a function of pit and uit plus summation over t equal to 1 to t, that we are now constructing the Lagrange function, the economic loop discussed that we have known, and we have using that conception we are finding the Lagrange function, that is function Lagrange function is a function of p, u, and lambda, that is the Lagrange constraint, equal to function of pit uit, that is the optimization function, plus summation over t equal to 1 to t lambda to the power t within the bracket p t load minus I1 to n pit uit. There is a load minus generation. It is multiplied with lambda to the power t over the time period t equal to 1 to t. And this is the objective function that we have already seen. So the unit commitment problem, it is required that we minimize the Lagrange function, that is subject to the local unit constraint 2 and 3, which can be applied each unit separately. That the 2 and the 3, that the local unit constraint that we have seen, and we have to minimize the Lagrangian function. The cost function, that is the function that we have already seen, that function cost function f is a function of pit and uit together with the constraint 2 and 3 that we have already seen are each separable over units. That is, what is done with one unit doesn't affect the cost of running other units as per the cost function and unit limits, and the unit up and down time, that is the cost function of the unit limits, that is the constant 2 that we have seen, and the unit up and down time, that is the constant 3, are concerned. Constant 1 are the coupling constraint across the units that we have already seen, so that we do to one unit affects what will happen on the other units if the coupling constant are unique. Means the effect of the one unit, what will affect the other unit. We will discuss a numerical problem in order to understand all those particular parameters. So the main conception of Lagrange relaxation, that is the procedure of Lagrange relaxation, that is solve the unit commitment problem by relaxing or temporarily ignoring the coupling constraint and solving the problem if they did not exist. So the main purpose of the Lagrange relaxation in the unit commitment problem is to relaxing or temporarily ignoring the coupling constraint and solving the problem as if did not exist. So this is done through the help of dual optimization procedure, and the dual procedure attempts to reach the constraint optimum by maximizing the Lagrangian with respect to the Lagrangian multipliers, while minimizing with respect to the other variables in the problem, that is q star lambda equal to maximization of q lambda at lambda to the power t, where q lambda equal to minimum of pit uit of Lagrangian function. So q lambda is the minimum of the Lagrangian function is given here, this particular part where the Lagrangian relaxation that is produced solve the unit commitment problem by relaxing the temporary, ignoring the coupling constraint. So there are two steps that we followed in order to do this. That is the find step one is a find a value of each lambda 2 which moves q lambda towards a larger value. And the step 2 is assume that lambda t that found in the step 1 are now fixed. Find the minimum of Lagrangian by adjusting the value of p to the power t and ut. These two steps left are adapted. So after adjustment of the lambda t values, we will deal with at a later time in this section that we will deal that assume that the value has chosen for all the lambda t and they are now to be treated as fixed number. We shall minimize the Lagrangian as follows. The Lagrangian function can be rewrite as summation over t equal to 1 to t, that entire time period, summation over 1 to n, that is the entire units, that is the function, cost function, that is the total cost function, that is f I p I t plus startup cost I t u I t plus t equal to 1 to t lambda t p load to the power t minus summation over 1 to n p I t u I t, that is the total Lagrangian function. Now this can be written as lambda equal to t equal to 1 to t I equal to 1 to n f I p I summation plus startup cost I t u t plus t equal to that 1 to t lambda t p load to the power t minus summation of t equal to 1 to t, this one I equal to 1 to n lambda t p of I t u of I t. In this way it can be rewritten in this way. So the second term in the above in this constraint can be dropped since lambda t are fixed. So finally we can rewritten the Lagrangian function. We can easily drop that particular term because lambda t is fixed. This is the second term, that p, lambda to the power t and p load to the power t is fixed. So we can easily drop that particular term and we can retain it in that particular way. That is Lagrangian is I equal to 1 to n summation over t equal I to 1 to t f I t p I t plus startup cross of I t, and it is multiplied by uit minus lambda t p I t uit. So here we can achieve our goal of separating the units from one another. The term inside the outer bracket, that is this one, this term that is clearly seen in the outer bracket, can be solved separately for each generating unit, and the minimum of Lagrangian is found by solving the minimum of each generating unit over all the time period. That is this one, minimum of q lambda is summation over I equal to 1 to n, minimum of summation over t equal to 1 to t f I t p I t plus startup cost of I t unit into uit minus lambda t pit uit, subjected to uit pit minimum less than equal to pit less than equal to uit pi maximum for t equal to 1 to t, and the up and down constraint. So this is easily solved a dynamic problem in one variable. This can be visualized in the figure below, which shows that only two possible states of the units are there. At ui equal to 0, the unit is in off condition, and ui equal to 1 is the unit that is in running condition, where SI stands for the startup cost for the unit I. That is clearly seen that at 0 and 1, this is the total startup cost. And again, it's come back to the 0, and again it's going up in this way, each for each hour, at our t equal to 1, at our t equal to 2, at our t equal to 3, at our t equal to 4. So at unit uit equal to 0 state, the value of the function to be minimized with trivial, that is the equal 0. At the state where uit equal to 1, the function to be minimized, that is the startup cost is dropped here since the minimization with respect to PIT. So there are two states that we have already seen. One is called UIT equal to 0 and UIT equal to 1. So the minimum of FIPI minus lambda TPI, that is the minimum of the function, is found by taking the, this is the, how we can find that by taking the first order derivative of that particular equation. And after derivative, the first order equation with ddt of pit, we getting that particular equation. So the solution of the equation is ddt of pit if ipi optimum value is equal to lambda t. To find the minimum value, we are doing a first order derivative of that particular equation with respect to pi. So it is clearly seen that there are three cases to be concerned with, depending on the relation of optimal pi value and the three unit limits. That if the pi optimal is less than pi minimum, then minimum value of that particular function will be if I pi minimum minus lambda t pi minimum, means pi became pi minimum if optimum value of pi that we have found is by that particular equation that we have already seen in our previous slide, that pi optimum value is less than equal to pi minimum. We are finding here the pi optimum value, and pi optimum value is less than pi minimum. So pi value is pi minimum. If pi minimum and if pi optimum is lies between the pi minimum and pi maximum, then this particular function will become the pi we became the pi optimum, and it will become fi pi optimum minus lambda t pi optimum. Means here, if pi optimum is less than the pi minimum, means the p-value that we will be write in this function, particular function, will be the pi minimum value. If pi optimum is lies between pi minimum and pi maximum, we are writing the in this particular function, we are writing the values of p as pi optimum. Is pi optimum greater than the pi max, then this function will become fi pi max minus lambda t pi max. Means we are writing in this function the value of pi max as a in the case of the p, we are writing the pi max. So this is the three cases that we are considering depending upon the relation on the pi optimum and the unit limits. So the solution of this two dynamic program for each unit process in the normal manner as we done for the forward dynamic program solution. So we are since that we seek to the minimization of particular function at each state and uit equal to 0, this value goes to 0, then only one way to the value is lower to have that particular function will be less than 0. The dynamic program should take into the account all the startup costs, that is the cost of SI for each unit as well as the minimum up and down time for the generators. Since we are solving for each generator independently, however, we have avoided the dimensionality problem that affects the dynamic programming solution. So another important part is how to adjust the value of the lambda. So the adjustment of the lambda must be done carefully to maximize the value of q lambda. So adjustment of lambda must be done carefully so as to maximize the value of q lambda. So lambda t, that is the new value of the lambda, equal to summation of old value of the lambda, new value of the lambda equal to old value of the lambda plus first order derivative of q lambda with respect to lambda into alpha, where the alpha is 0.01 when this particular dt lambda of q lambda is positive and alpha is 0.002 when dt lambda of q lambda is negative. So this is the way that we can adjust the value of lambda. So another important factor called the relative duality gap, that is given by J star minus Q star by Q star. So the relative duality gap is used as a measure of closeness to the solution. Means when we will see that when we will do a particular problem related to Lagrange relaxation, we will see that how we can apply the conception of and lambda adjusting or the conception of Q lambda, and also the how we can uh, apply the concept of relative duality gap, that is the relative duality gap that is used as a measure of the closeness to the solution. For large real-time power system unit calculation, the duality gap does become quite small as the dual optimization process, and its size can be used as stopping criteria. The larger the problem, larger the number of generating units, the smaller is the gap. The convergence is unstable at the end, meaning that some units are being switched in and out, and the process never comes to a definite end. There is no guarantee that when the dual solution is stopped, it will be a feasible solution. But the relatively dual gap, or the generally used as a measure of closeness to the solution, how we get more closer to a particular solution. So that is the general flowchart for the Lagrange relaxation procedure that is given that we are starting with a peak starting with lambda t for t equal to 1 to t and the k equal to 0. The next step is for each unit I. Third one, we have to build a dynamic program having two states at t stages and solve for PIT and UIT for all t equal to 1 to t. Last unit done. If no, then go to that particular and go back to that particular segment that is for each unit I. If yes, then solve the dual value of q lambda, q star lambda t. And using the second step is, in another step is that when I calculate the value of q star lambda t, the next step is using the ut, calculate the primal value of j star. That is solve the economic dispatch for each hour using the units that have been committed for that hour. Then we have next step is calculate the relative duality curve that is j star minus q star by q star. If update all lambda t, update lambda, next step is update lambda t for all t and then move back to that particular path that is for each unit I. And if the relative duality gap is sufficiently small, if yes, then make the final adjustment to the unit commitment schedule to achieve feasibility and the program. And we have done the particular Lagrangian relaxation procedure. This is the flowchart. Now we are taking an example in order to understand that what we have learned till now with the help of an example. There is a 3 generator 4-hour unit commitment problem, means capital N equal to 3, capital T equal to 4. So there are 3 generators and the 4-hour unit commitment problem will be solved. The data is provided for the 3 generating unit, that is F1 P1 equal to 500 plus 10 P1 plus 0.002 P1 square, where P1 is lies between 100 to 600. F2 P2 equal to 300 plus 8 P2 plus 0.0025 P2 square, where P2 is lies between the 100 to 400, and F3 P3 is lies between equal to 100 plus 6 P3 plus 0.005 P3 square for the 3 units, and the P3 is lies between 50 to 200, the cost functions, and along with the load are given at T equal to hour 1, 2, 3, 4, the corresponding P load to the power T in megawatt is for first hour it is 170 megawatt, for second hour it is 520 megawatt, for third hour it is 1100 megawatt, for fourth hour it is 330 megawatt. So these are the cost functions, and along with the given data for the 3 generating units and along with the load pattern are given for the 3 generating units. So we have to solve a problem with the conception of Lagrange relaxation problem so that we can easily understand the conception of Lagrange relaxation. So now, to solve this particular problem, we are starting from the initial condition where lambda t values is set to be a 0, means lambda t equal to 0. So here we have seen that the N, capital N equal to 3 because 3 units are there, and the 4 hours means capital T equal to 4, 1, 2, 3, 4. And we are solving this with the conception of Lagrange relaxation technique, where we are putting that first the initial condition is that starting from initial condition where we put lambda to the power T equal to 0. The economic dispatch is run for each hour, provided there is sufficient generation that is committed to that hour. For each hour, we are apply the knowledge of economical generation or economical load dispatch conception. If there is not enough generation committed, the total cost for that hour is set arbitrary to 10,000. Again, I am telling that if there is not enough generation is there, so we can easily say that the total generation of that particular total cost for that hour is set as arbitrary to 10,000. Once each hour has enough generation committed, The primal value of J star is simply represent the total generation cost sum over all the hours calculated by the economic dispatch. If there is not enough generation, we can take an arbitrary value of that hour is set by 10,000. If there is a generation is there, we just apply the knowledge for that particular hour. We just apply the knowledge of economic dispatch to calculate the total cost for that particular hour in order to calculate the value of J star. That is given J star simply represent the total generation cost summed over all hours as calculated by the economic dispatch. So let us start with lambda t equal to 0. When lambda t equal to 0, all the values are zeros, means the hour always, for each hour will always result all the generated units in of light. So that is the there is no generation, so P load to the power t, which is minus summation of 1 I summation of I equal to 1 to n pi t u by t, that is p load t minus summation over 1 I 1 to n pi t u by t will become that particular string because there is no generation, all the loads. So 170 minus 0 is 170, 520 minus 0 is 520, 1100 minus 0 is 1100, and 330 minus 0 is 0. So q lambda value is 0 and the j star value will be, there is no unit. If it is clearly written that if there is uh, not enough generation committed, the total cost for that hour is set to 10,000. So there are 4 hours, so total J star will be 4 into 10,000, that is 40,000. And the value of J star minus Q star by Q star equal to undefined as Q lambda equal to 0. That is 40,000 minus 0 by 0, it will be undefined. Then in the next iteration, the lambda 2 value has to be increased. Now we will see how we just increase the conception, increase the value of lambda t. What is the mathematical calculation behind that lambda t approach? So, uh, to illustrate the use of dynamic programming to schedule each generator, we will start the DP steps for the unit 3. So, it is there, we are generally dealing with the two conditions. If I follow that particular graph pattern, one condition when at our t1 equal to, at our t equal to 1, that's the first hour, the unit 3 is off condition. The second hour unit 3 is on condition. Third hour unit, the first hour unit 3 is off condition. Second hour unit 2 3 is also in the off condition. At the hour 3 the unit t is on condition, and hour 4 unit 3 is also brought to the off condition. So for 1, 2, and 4, they are in off condition, unit 3, and at t equal to 3 hour 3, the third hour, the unit 3 is on condition. So there are those values of the lambda that we have obtained: 1.7, 5.2, 11.0, and 3.3. How we can obtain that particular value? So let us first concentrate on that calculation. When unit 3 is off, at the calculation for Fp minus lambda p for unit 3 at t equal to 1 means the first hour, the unit 3 is off. So from that particular equation, the minimum value of unit 3 is 50. Minimum generation capacity is for the unit 3 is 50 that we have seen. So the P3, that is the, became 50, and say lambda is 1.7. We will see that how these lambda values are come in the second iteration, that we will see definitely in our next slides. So the value of the F3 became, this is the general cost equation for the F3, that is 100 plus 6 P3 plus 0.005 P3 square, and limit is there given. So Fp minus lambda P, that is became 100 plus 6 into 50 plus 0.005 into 50 square minus 1.7 into 50, that is 327.5. At t equal to 2, the value of lambda is 5.2, and also the unit 3 is off condition, so value of P3 will be 50, and putting those values in this equation, we are getting it is 152.5. Now at t equal to 3, the unit 3 is on, so the value of P3 will be 200 and lambda is 11.0. Just putting those values in this equation, just putting those values in this equation of P3, that is 200, and the value of lambda into P, that is 11.0 into 200, we are getting the value of minus 700. At t equal to 4, again the unit 3 is in off condition, so value of P3 is 50 and lambda is 3.3. Just putting those values of P3 in this equation, the fuel cost equation, and it and minus lambda into P, that is 50, that is 247.5. So here the different values of lambda, this calculation that we have already seen. So that is means that what we have done in this, what we have learned that the three feasible condition that we have when it is on, that is it is positive means P3 1 equal to P3 minimum value that we have already seen. And when at equal to 3, that is positive means P32 is P3 minimum value, and it is now negative, that is minus 700. So P33 has P3 maximum value, and when again it is plus 247.5, so P43 is at P3 minimum value depending upon the values of Fp minus lambda p. When they are in positives, plus 327.5 plus 15255, the value of P3 is at P3 minimum. But when it is negative now, minus 700, the value of P3 at our 3 is, for the first hour, the value of P3 will be P3 minimum. For the second hour, the value of P3 will be P3 minimum. But for the third hour, the value of P3 is P3 maximum, that is 200. And minimum is 50. Because the value of Fp minus lambda p at t equal to our 3 is minus 700. And when again at t equal to 4, the value of P3 is P3 minimum. That we have already seen in that particular. This is the way that we have already seen in this particular equation, how we can easily design with the help of that particular optimal value. And how we can design, we are seeing with the help of that particular example. We can easily see that particular portion. The three conditions that is satisfying, we can easily see that three conditions of satisfying that how that three conditions are applied in a problem that we have already seen in this equation. Now, another part of that is given by, so this is generally known to us. Now we will discuss about the next table, how we can calculate the value of lambda, how we adjust the value of lambda that we have seen. Now we will see that how we can adjust the value of lambda. So that particular three parameters, the optimal value of p depending upon the limits and depending upon the value of fp minus lambda p that we have already seen. Now the result is to schedule the unit 3 off during the 1, 2 and 4 hours and on during the hour 3 that we have seen, that how we can schedule a unit depending upon the value of Fp minus lambda p. For each of the unit, depending upon the values for each of the hours, Fp and the lambda p, we will schedule the unit. Further, unit still 3 is scheduled to its maximum value of 200 megawatt that during hour 3 that we have already seen. The result after all the units have been scheduled by DP are follows. Means now in this particular way, we have seen that how we can schedule a unit 3. So in this particular way at hour 3, we can easily schedule each of the units. So here in this iteration 2 table, It is clearly seen that we are scheduled at hour 3, the unit 3 and unit 2. So first we will concentrate on the particular calculation, how we will calculate the value of lambda. This is our main object. So in order to calculate the value of the lambda, this one, lambda k plus 1 equal to lambda k plus dd lambda of q into alpha, where when this portion is dd lambda k plus dd lambda of q plus alpha, this dd lambda of q, the first order derivative of q with respect to lambda, objective function with respect to lambda, is positive, the value of alpha is 0.01, and when it is negative, the value of alpha is 0.002. Now for the t equal to 1 hour, let us concentrate for the table 2, how we can adjust the value of lambda. Now, if I concentrate on the table 1, we will see the value of, if I concentrate on the table 1, we will see that this is the value of q, q lambda. This is the value of q lambda, this portion. This is the value of uh, p dot to the power t minus summation of 1 I1 to n pit uit. PIT, UIT. So you will concentrate on that particular part. So all are positives. Here all are positives. All are positive values. So means the alpha value for the iteration of lambda in the next table will be 0.01. So for the time 1, that is the first hour, the lambda 2 stands for the next iteration, that's the second table iteration. There's the previous value lambda 1, that is we are considering 0, plus that value we have seen in that table, it is positive 170 in the table 1. So it is 170. If it is positive, then the value of alpha will be 0.01. So 170 into 0.01 is 1.7. At our 2, the value of lambda 2 is lambda 1 plus, we are following the same formula. So it is 0 plus 520 into 0.01, that is 5.2. For the third hour, it is 0 plus 110 plus 0.01, that is 11. For the fourth hour, it will be 0 plus 330 into 0.01, that is 3.3. In this way, we are calculating the value of lambda in the table 2 from the table 1. From table 1, we can easily find that all the values, that is plus 170, plus 520, plus 1100, plus 330, those values are positive. That is why we are taking alpha as 0.01 in order to calculate the new value of the alpha in second table, iteration table. So this part, also you see that particular part, how we can find the value of new alpha, that is the adjustment of alpha, with the help of a calculation. So, and this particular portion that we are obtaining, that all are positive values, and we are multiplying alpha with that and summating with the previous value of the alpha, this one 0 plus 170, it is positive, into 0.01, 0 plus 520 into 0.01, 0 plus 1100 plus 0.01, this is 0, the old value of the alpha. For our 4 is 330 into 0.01. So in this way, we just calculate the new values of alpha for the second iteration, that is 1.7, 5.2, 11.0, and 3.3. Now, the value of P2 and P3 is known to us, that is 400 and the 200, that is P2 and the P3 value is 400 and 200, that is known to us. Just putting those values, 400 and 200, and it is clearly seen that the total value of q lambda, how we calculate the q lambda. This is the another part, that how we calculate the q lambda portion. So, and it is clear that in order to calculate the q lambda, we are concentrating on that first hour, no unit is committed, second hour, no unit is committed, At third hour, unit 1 and 2 is unit 2 and 3 is committed, and in fourth hour, no unit is committed. So only at hour 3, unit 2 and 3 is committed. So that is the calculation for the Q lambda in the second iteration. That is, we are concentrating on the unit 2 and the 3. This is the general equation for unit 2 and the 3. That's two equations that we have get. These two equations. These two equations we are taking unit 2 and 3. These two equations. Unit 2 and unit 3. So these two equations, just we have written those two equations, putting the values of, just written those two equations after putting those values of P2 equal to 400 and P3 equal to 200. These lines will give that particular equations plus 1.7 into 170, that is the lambda value, plus 5 point into 170, that is the value of P load minus generation, plus 5.2 into 520 plus 11 into 500 plus 3.3 into 330. That is why we are finding the value of Q lambda, that is 14,982. So in this way the Q lambda is calculated. So here this is 14,942. So just putting the values of P3 200 and P2 400 in those two equations plus 1.7 into 170, 5.2 into 520, 11.0 into 5, 11.0 into that particular thing that is given here, 11.0 into 1100, and it is clear that 11 into 500 and 3.3 into 330. So that is nothing but all that particular equation means the equation that is putting on the fuel cost equation, values of P1 equal P2 equal to 400 and P3 equal to 300, or in those equations plus 17.170, 1.7 into 170, 5.2 into 520, 11.0 into 500 plus 3.3 into 300. In this way the Q lambda is calculated. So the values of J star will be 4000 because it will be cleared from the previous that 4 into 1000 equal to 4000, 4 into 10,000 that is 4000. So values of J star minus Q star by Q star that also been calculated here. The values of J star minus Q star by Q star, that is 40,000 minus 14982 divided by 14982, that is 1.67. This is the calculation of J star. So here it is clearly written that the calculation of the J star is in that way. And there is a P load, there is no generation, so it is 170 minus 0 equal to 170. It is 520 minus 0 equal to 520. And why this is 500? Because here the load demand is 1000, so P load demand is 1100 for the hour third. For the third hour, the load demand we have seen in the problem is 1100. So it is 1100 minus 400 plus 200, that is 600. So 1100 minus 600 will be 500. And here there is no unit is generated, so it is, that is load minus generation, that is 1100 minus 600, that is 500 for the third hour. For the fourth hour it is 330 minus 0 equal to 0 equal to 330, that is 330 because there is no generation. For the first, second and the fourth hour, this PIT UIT summation over 1 to n is 0, so only the load value is coming here. For the third hour, this generation is 400 plus 200, that is 600 for the 2 units, so it is 1100 minus 600, that is 500. And you know how you can calculate the Q lambda and how you can calculate the J star and also the values of J star minus Q star by Q star. So another thing for the iteration 3, that we will go for the iteration 3 for the values of the lambda. From here it is clearly seen all are positive, so we will put the values of the lambda as values of, in order to calculate the new value of the lambda, the values of alpha will be 0.01. So we will see for the iteration 3, the new value of the lambda 3, that is 1.7, the old value from the table 2, 170 into 0.01, it is alpha equal to 0.01 because all the values are positive. So that is 3.4. Same way it is 10.4, 16, and 6.6. For the 16 it is 11 plus 500 into 0.01, 16, and for it is 6.6 for the hour 4. So from that table, it is nothing but 1.7 plus 170, it is positive, into 0.01, 5.2 plus 520 into 0.01, 11.0 plus 500 into 0.01, 3.3 plus 330 into 0.01. In this way, the entire new value of the iteration 3 table, entire new value of the alpha is calculated. Here we see that we are committed another 3 units at our 3. At our 2, we are committed the 1 and 2, 2 and 3 unit, and at our 3, we are committed the 1, 2, and the 3 unit, all the 3 units. So here it is the output is 400 and 200, and here it is output is the maximum power for the P2 and P3 is 400 and 200, and P1, P2, and P3 at our 3 is 600, 400, and 200. So here it is, the load is 170 minus 0 equal to 0 because there is no generation. Here the generation is 600, and the load is, now the load at the hour second is 520. So it is 520 minus 600, it will be minus 80. Here the generation is 1200, and the load at the hour 3 is 1100. So it is 1100 minus 1200 is minus 100. And for the hour 4, there is no generation is there, so it is 330 minus 0 equal to 330. So another approach is that how we can apply the conception of economic load dispatch. So in order to take the conception of economic load dispatch, I am taking at our 3 equation. So our 3, how we can find the P1 ETC, P2 ETC, and P3 ETC. In that way, that all the this for each hour, for the hour 1, hour 2, hour 3, and hour 4, this value is calculated. I just give you an example how to calculate at hour 3 the value of P1 ETC, that is economic dispatch of generator 1, generator 2, and generator 3. So it is clear that the calculation of P1 ETC, P2 ETC, and P3 ETC. So at hour 3, the load demand is of P1, P2, and P3 is 1100. From there, P3 is generating the 200 unit. It is clear from our previous lecture also that how we can recommend the P3, because it production cost is, average fuel production cost is more, so we can make so less amount will be generated by the P3. So P3 is generating the 200 unit, so it is remaining that P1 plus P2 equal to 1100 minus 200, that is 900. And another is that the we are approaching to the economic load dispatch conception. So first order derivative of F1 equal to first order derivative of F2 with respect to P1 and P2, that is ddP1 of F1 P1 equal to ddP2 of F2 P2. When we are applying the conception of the economic load dispatch, just putting those values, the F1 and F2 equation here, we are getting this equation 0.004 P1 minus 0.01 P2 equal to minus 2. From that two equation, that is equation 1 and equation 2, we are getting the values of P1 equal to 500 and P2 equal to 400, and P3 is obviously 200. So this is the way we are calculating the economic load dispatch, that is 500, 400, and 300. And for the each economic load dispatch conception, these values we are putting at the equations of P1, P2, and P3 for each hour and summing those particular values, and where there is no generation is there, we are taking the cost of 10,000 and summing those for each and hours, we are finding the values of J star. So for in this way, you are calculating the values of this one. Now for the table 4, there are two minus sign, means for that two calculation we will find, we will take the alpha value of 0.002. So for the table 4, we are calculating the alpha value. That is, for the first hour, it will be given positive because it is plus 170. So 3.4 plus 170 into 0.01, that is 5.1. For the second hour, second hour, the value of lambda 4 will be minus 80, and that is why we are taking the alpha value. When it is negative, it will be 0.002. So it is 10 plus 4 plus minus 18 to 0.002, it is 10.24. For the third hour, it is again negative. So we are taking the alpha value is 0.002. So it is 16.0 plus minus 100 into 0.002, that is 15.8. And the fourth hour, that is lambda 4, it will be again positive. So alpha is taking 0.01, it is 9.9. So that is why in this way that is calculated. That is 3.4 into 170 into 0.01, that is 5.1. 10.4 into minus 80 into 0.002, and 16.0 plus minus 100 into 0.002, and 6.6 plus 330 into 0.01. The values are 5.1, 10.24, 15.8, and 9.9. And how we can calculate the q lambda in this equation? Q lambda can be calculated at hour 2 and at hour 3. At hour 2, only unit 2 and 3 are there, and at hour 3, unit 1, 2, and 3 are there in operation. So Q lambda can be calculated here in this way. We are just writing the equation of P1 equal to 600, P2 equal to 400, and P3 equal to 200. This equation is, these first three terms can be done for the all the three units at running condition for hour 3. For hour 2, this when the unit 2 and 3 in running condition plus 3.4 into 170, 10.4 into minus 80, 16 into minus 100, and 330 into 6.6, that is Q lambda value is 18,344, and J star Q star value is 36024 minus 18,344 divided by 18,344, 18344, that is 0.965. So here in this way, we can easily find the value of Q lambda that we have seen for each hour, summation of that particular values for hour 2 and the 3, and this equation followed by the J star values and the values of J star minus Q star by Q star. In this way, we are doing the sixth iteration. In the same way, we are doing the each of the iteration and the calculations. So from there, after 10 iteration, we are getting the Q lambda value is 19,485 and J star equal to 20,017. So J star minus Q star by Q star, that is given that 0.027. So the later value will not go to 0, not will the solution settle down to a final value. Therefore, we have to stop the algorithm when J star minus Q star by Q star is sufficiently small, that is less than 0.05. In this case, we have to stop that particular algorithm. In this way, we have done the iteration. So today we have learned about the Lagrange relaxation solution and how we can do the unit commitment problem, or how we can solve the unit commitment problems with the help of Lagrange relaxation solution. Thank you.